All right, welcome back again. We'll start by talking about what's going on this week, which is there's a homework due on Friday. Have you had a chance to try the homework yet? Anybody tried it? Was it challenging? Not the model part? How about the Bayes part? The stand part okay? Excellent. So you're able to build a model, build multiple models, get them to compile, get them to run. Awesome. How many of you use the matrix version of the code that I showed the last time we met? Yeah? So. Fair. That works. Okay. Any questions then on homework? I'll just ask one more time. See, I always have to do something when I ask a question. JC, yes. Yeah. Let's see. Hang on one second. Let me share my screen. And I'm going to grab the homework real quick. Or try to at least. My mouse is going somewhere else. All right. Thinking about it. I don't know why Word takes the longest to open on my Mac, but it does. And of course, when it opens on a different screen. Here we go. Okay, which part? Oh, that's homework 1. What am I doing? My goodness. I'm sorry. Which part was it again? Okay. Okay, just a moment. Somehow my iPad screen is interfering with my mouse, which is killing me. All right, hang on one second. Okay, the last part. Oh, this part right here. Yeah. Great question. Let's see here. Write a results section. So basically what I was trying to say was if you... the blanks here... This result section that I'm giving you here is a template. It's not really what you have to use. So my thought was basically you could follow along, you can borrow the text, but where the blank sections are, if you wanted to follow along, you could. Blank section, these are numbers that you fill in from the results that you have above. And so my questions for you are to go and figure out, so for instance, when it says the baseline manifest model counted for blank amount of variance, this would be a proportion, right? So you'd have to go figure that out from your different values that you did before. The purpose for this question is to get you to think about how to write about Bayesian results. There's not a lot of differences because they're very similar to frequentist results. But the bigger picture was this was a sort of a rough guide. I'm not as nice as Lisa, and I don't give you the drop-down boxes, but this is more of a question for you to sort of fill in as you go, and these are sort of a way to do it. Does that make sense? Right. You can write your own version of this. This was just taken from one of her homework systems to build that. Excellent. Thank you. Other questions about homework? Okay. I'll just assume there's no questions and we'll move on. Remember, homework will be due on Friday. Anytime before 11:59 p.m. Friday. So literally any time on Friday. And then I will return that to you next week. Okay? Boom. Looks like we're good. Thank you for nodding in approval. Next. I left a video to watch last week. Just one lecture. Lecture 3C. It was a great video. I mean, it was one of my best. Don't you think? I'm just kidding. Normally I come in here and I try to pick on myself, and now I'm just going for straight confidence, right? That was one of my better works. Now, with it being one of my better works, I realize I probably should ask you about it. So let's talk about it a little. See, I'm being sarcastic. I don't know if it was very good or very bad, but I do know the contents of it. It was talking about how we assess relative and absolute model fit in Bayesian statistics. Did you watch that video? Did you have a chance to watch it? Excellent. If I were to ask you a little bit about, like, for instance, what would you say an absolute version of a model fit statistic would be in Bayes? What would one acronym come to mind for it? And this is absolute, telling whether your model fits the data in an absolute sense. Erica says LOO. Not quite, sorry. That'll be relative. PPMC, yes, PPMC, posterior predictive model checking. So, what did you think of that method for model fit overall? Many of you have been in other classes where we're like, and the model fit index is the RMSEA. Here, boom, here it is, it's a number. PPMC doesn't work like that. What'd you think of it? Conceptually. You like it? Does it seem sketchy? As my kid would say, does it seem sus? You know, he likes the Among Us. I don't know. I always found PPMC to be awesome. Maybe that's because I drank the Bayesian Kool-Aid and I'm part of the Bayesian cult now. But I think PPMC is great, and you can think about why, right? Basically, you fit a model and then you generate data from it using simulation methods. And if that data looks like the real data, it sort of suggests your model and the real data work well together, right? So can you envision ways that you could use PPMC, for many models? For instance, the homework I gave you this homework doesn't have, it's a straight linear model. And if you remember linear models class, I'm scrolling through it as we talk here. If you remember linear models class, we didn't talk about model fit there, did we? Some classes call R squared model fit, but it's sort of like, I guess it's a version of model fit, certainly. But at the same time, it's not whether or not you can believe the model and that fits the data. So if we didn't talk about model fit, like a PPMC version of model fit in linear models class, why do we need to worry about it in Bayes class? I'm going to do this. I'm not going to share anymore. I'll just look right at you, right here. I asked terrible questions, I know. So let me rephrase, okay? Okay. In linear models, linear regression, ANOVA, ANCOVA, not MANOVA, but the univariate linear models. We never talk about model fit, do we? And yet in Bayesian, I used it to check a linear model. So one of these things either must not be like each other, right? Univariate linear models and Bayesian linear models, or at least slightly different. Or there's something different about one of them that causes you to make you wonder, does my model fit the data? What do you think it might be? Aha, the priors. Let's give a thumbs up for that one. Can I do it? No, reaction. Hang on. Let's get a reaction going. Here we go. Yes. Good answer. The priors. All right. So think of it this way. You've seen it. When I was playing with priors with you, we put those really informative priors on a linear model, and the variance the residual standard deviation went super large, right? And then we decided to put a really informative prior on it, and it got shrunk down a little bit, and the fixed effects for the model for the means, the regression coefficients got super large, or somewhere in between, right? Well, you're right. In that sense, that the priors can help, the priors in Bayesian can be so informative that your results look nothing like the data, which is a problem. So in a non-Bayesian application, if we use least squares or maximum likelihood, we're sort of guaranteed that we will get close to the data, even if it's in a linear model sense. What do I mean by that? The regression line will go through most of the points. There may be there may be points that leverage it, that make it look sort of the line. If you have a cloud of data and you have one point on the outside, it might pull the line up. We can calculate leverage values and so forth. But generally speaking, from a model sense, the univariate linear models fit the data well, right? The residual variance is what's left over. There's nothing model fit-wise that we really describe. But PPMC is needed for Bayesian to check our priors. Exactly. On that note, as we go from the univariate version in linear models, today we're going to start talking about psychometric models and how we're going to put those into Bayesian methods. Once you go from one outcome to two, once you go from univariate to multivariate, two or more, model fit becomes an issue, because now what you end up having is sort of a residual covariance matrix or some type of covariance matrix. And if you don't approximate that well, turns out it's possible a linear model may not approximate it well, or even a psychometric model. And if it doesn't, then you may have problems with misleading point estimates of your parameters. In our case, the prior distributions will be a little bit off. So something to quantify, something you don't see in linear models very often, but in Bayes, because of our priors, we have to worry about. All right. Any other questions on any of this? No, it seems like everybody's saying, just shut up already and get to the lecture. Am I right? No, I do have to keep teaching for the next hour, but I will do so with a lecture in front of me. All right, let's get to the lecture then. Okay. And, I should also mention before I completely dive into the lecture that the ideas of PPMC and then the relative model fit statistics, WAIC and LOO-PSIS, Pareto Smoothed Importance Sampling, those are going to keep with us throughout the class as well, too. And you are fortunate to be taking a Bayes class in the year 2024, because both of those statistics are very good at detecting model comparisons. Vladimir, question? Yeah, so the idea would be, to me, and I'm going to give you the idea in a very non-technical manner. How's that sound? Sort of a broad, high-level understanding. The person likelihood, right? So your person likelihood takes your model parameters from any point of the Markov chain, puts it into the model data likelihood with the data, and calculates how likely that is for each person. What that tells you is how far off a person might be if the likelihood is big or small. And if we take it from the leave one out perspective, right? So it gets a little bit different when we approximate leave one out. But if we take our 30-person example from our previous class and we just left one observation out and we calculated the model with 29 different observations, and then every step of the chain calculated the 30th person's likelihood. What that would tell us is how close we are, or how likely that model fits for a given person. Basically, it's like a person fit statistic, right? And so if we end up having one or more persons whose likelihood values are so very far distant from the rest, that sort of indicates that those folks may have an undue leverage or influence on the rest of the model itself. Now, in practice, what that really means is when we fit a model and we calculate LOO or WAIC from it within the model, we're not actually removing anybody, doing the leave one out process. LOO, the leave one out process, that's where this latter part of the acronym comes from. Pareto Smoothed Importance Sampling, PSIS, tries to look at those values of person likelihood, so basically person fits, if you want to call that, and talk about how they would have looked had we left that person out overall of like a cross-validation approach. Thank you. So this idea of likelihood-based fit, to me, we see this in several other places, at least in the psychometric literature that I'm familiar with. One is item response models. We talk about person fit to item response models. You can talk about in Roche modeling, there's in-fit and out-fit. But then there's a bunch of other person fit work in other areas as well, again, a cross-validation step. The other place I've seen it would be in mixed models. So in proc mix, there's actually a influence option if you get into SAS. Influence being, remember, I mentioned if there was an individual if you had a bivariate regression and there was one outlier, right? It could leverage the regression line to move in a different spot. In the proc mix version of this, because you may have multiple observations per person, the likelihood is used instead. So basically looking how a collection of person observations may be different from everything else. And so the thought with it being that what you're trying to see is if a model doesn't fit a set of people or a group of people, this statistic will be larger or will be farther off, and that's what we're trying to quantify, was how well each person's likelihood behaves like the rest, I think. So that's a high-level description of it. Does that help answer your question? You're welcome. I will note that the math behind both the WAIC and LLO is kind of intimidating, kind of daunting, even for myself. So, but I think I left a link for you for the original work for those papers if you'd like to go try to trace those down. But I do think both of those methods are also nice, and because let's just talk about them in comparison to the model fit index I grew up with in Bayesian, which is called deviance information criterion, or DIC. The DIC would cause you to take basically the likelihood of the model, given your point estimates of your parameters, and then those point estimates themselves involving averaging. Basically, what's the average parameter value? That was a problem because in many models you may not have that average itself may represent a point that's not possible in the model. So for instance, if you have a classification method and you're classifying a person as group 1 or group 2, the average will be the probability they're in group 1 or the probability they'll be in group 2. There's no one on one side, one on the other. And so that DIC issue was somewhat problematic from a model fit perspective, even though it behaves very similarly in the limit to WAIC and LLO. Oh, did I see another question, James? No. Okay. Cool. Hopefully that answers the question. Are we good? Yeah. The nice thing about likelihoods is that within a model, the model data likelihood itself, the likelihoods are all on the same scale. So it's easy so a person evaluating a person's set of data versus, for one person versus another returns a number that's comparable, which is helpful. Where things get off is if that likelihood function is different for different people, right? So if we have a normal model or some type of normal approximation for part of our data and we're comparing it to something that's maybe a binomial approximation of normal or something, some crazy other distribution, those distributions likelihoods aren't easily comparable. So within the context of similar families of models, they are, and that's what we end up using a likelihood for. All right. I keep talking about likelihoods. They're the magical part of statistics, though. They sort of drive everything for what we do. And you wouldn't even know about them if all you took was linear regression, because we do least squares there. You don't even hear about likelihoods. But we'll leave it. Leave it now. All right. Other questions? All right. Let's dive in then. I was told, and I think you probably saw it too, that our high-performance computing system would be down for maintenance today, but it appears to be working. So I'll try to give the lecture actually, I'll just go back to just in case, I'll go with the slides. The lecture today is conceptual in nature. And this is sort of the issue I had with teaching this class. As I mentioned, right, we got to teach you Bayes, and I got to put it in the context of psychometrics and the way I talk about it. So we iterate between those two. Well, the last time we talked about linear models, because everybody should be mostly familiar with linear models, and then we put them in Bayes. And now what we're going to do is talk about psychometric models, and then for the remainder of the class, we're going to put them in Bayes. Okay? Cool. So today's class is the mathematical introduction to the psychometric models. I call them generalized measurement models. It's probably more jargony than it needs to be, but the word generalized to me is used when we talk about observed data distributions that aren't just normal. So in our case, some psychometric models assume our observed variables are normal. It's like a confirmatory factor model. And some don't, like item response theory, which is binary usually, or categorical. But all of them are trying to measure some type of latent variable. That's where measurement model comes in. So when I see generalized, when I decode that, you would expect to see distributions that aren't just normal. So normal, categorical, Bernoulli, name it. And when you see measurement models, what you can think about is a model data likelihood that involves both, one, the data, because it needs to be there, and two, a set of latent variables that we're trying to measure. So the idea of measurement models is that this is a model that says, had we have observed this latent construct, we would be able to predict how well it does predicting our data, right? It's measurement from a sense. All right, so today we're going to try to talk about measurement models in general. Again, I'm giving you this in a generalized framework. I think what you could see about today are all the models that we talk about in here are going to be versions of ones that you'd see in Lisa's SEM class or somewhere between SEM and item response theory. Although, as you know with Bayesian, any one of the distributions that you saw in the Stan manual could be used to build a measurement model. But this is sort of the general framework that we're putting it in. We're going to talk about the steps needed in a psychometric model analysis. As you know, that works a little bit differently than linear regression. And we're going to dive deeper into the observed variables version of the modeling itself. Okay? Please stop me if you have questions, as always. All right. Oh boy, there we go. I used this example data for several years now, and I'm sort of thinking of retiring it, given the state of the world that we're in. It seems to me that in the last, I don't know how many years, everything that the broadcasting of widespread conspiracy theories is ridiculous, right? So everything from being able to control the weather to who knows what. So I give this example from a data set that were collected in the early 2010s. And this might bring you back down conspiracy theory lane. I just thought it was a funny example, but I'm kind of disgusted with the way that conspiracy theories sort of run wild now. So I might just remove this from next time. But today we've got to deal with it. So long story short, I was given a workshop in Boulder, Colorado for the ICPSR, which is the Intra-University Consortium on Social and Political Research. They had a summer school program. I was teaching IRT, I think. It might have been a different topic, but one of the students there I was talking about, for those of you who know Colorado, the Denver airport has had these conspiracy theory / urban legends for many years about it. You can go Google it online. We don't need to get into much of it now. There's just a bunch of weird things at the airport that made people go, this is just strange. Anyway, so I mentioned this, and next thing you know, one of the people in the class said, hey, I actually study that, and I have some data. Would you like them to just play around with for an example? So I said, yeah, let's do that. That's great. This was, again, back when it just seems like life was so simple. It wasn't that, a hurricane would hit and we'd be, making conspiracy theories about it or every single thing that you look at anymore. So let's just think of this as if we were in the early 2010s, back before, I don't know what. Anyway, so there were 10 questions. Their responses were Likert type responses, we call it. So these were, you had to pick an option, participants had to pick an option: strongly agree, disagree, neither agree nor disagree, agree, or strongly agree. The numbers 1 through 5 get attached to those. And the 10 questions I'm about to show you in just a bit here, what the purpose of this study was to find individual. Here's the disclaimer. The purpose of the study was to study individual beliefs regarding conspiracies. The questions can provoke some strong emotions in the world we live in currently, and I will note that all questions were verified by the IRB. So let's just see this here. Questions. And again, this is making me uncomfortable, so maybe I should probably not use this, but the U.S. invasion of Iraq was not a part of a campaign to fight terrorism, but was driven by oil companies, and anti-Semitism behind that question. Certain U.S. officials planned the attacks of September 11th. Barack Obama was not really born in the United States. That was a huge one at the time. That was disgusting. The financial crisis of that time was Wall Street bankers. Basically, the gist of this, right? Chemtrails, someone trying to be behind this George Soros and American media. There was a conspiracy theory about fluorescent light bulbs. You ever see that one? I don't know if you've seen that one before. Or the NAFTA superhighway. That was a big concern back then as well. The 1980s conspiracy, or actually, maybe conspiracy. And then somehow using a hurricane to damage us. Anyway, I need to retire these data. Here is what we've seen in these responses. The bottom line is that for every one of these item responses, predominantly most people said absolutely not. And back in 2010, it may be assuring to you to know, or the early 2010s, that the hurricane response, the one, was strongly disagreed by almost everybody. That's the point. But these data for me provide us a nice example for psychometric data, because if you ignore the questions and you just know that you have 5-point Likert scales, the first question I would have for you is, how would you model this, right? Things that we have to think about. Plus, you don't have to answer that. That's not a formal question, but just be thinking about, how would I model these data? What do I need to think about first? How do I build that? So using this is my guide for how we use measurement models. So here are the measurement model analysis steps I like to think about. Number one, we specify a model. Turns out that is the psychometrician in me talking, right? That's the mathematician. I'm not really a mathematician, but the person who studies the methods behind it. Really, before we specify the model, we need to think about what we're measuring. What is the construct, right? And so once we understand the construct or constructs, is there one of them? Is there more than one of them? Once we put down a plan for what we're trying to measure, then we specify the model that maps onto that plan, right? That part, specify model, is really what we're talking about in this class. How do we build code to estimate a confirmatory factor model or an IRT model, right? But we're going to start a little bit by construct. So when you see specify model, that really means we've identified and enumerated a construct to measure, or more than one construct, and we've mapped that onto the items that we had before. Once we specify the model, though, then we have to make some decisions. The first is for a latent variable model. We don't observe the variable itself, so we have to determine its scale, right? We need to figure out what its mean is, what its variance is. How do we identify that? We call it scale identification, or at least I do. And then we estimate the model, step 3. And if the model doesn't fit, we usually go back and iterate. We respecify the model and the other steps, and we successively do multiple models until we get adequate fit. Perhaps you've seen that process before. I will say step 5 is the part that makes statisticians and other folks who do quantitative methods a bit uncomfortable, because in theory, when we falsify a model, we're done. We shouldn't be data snooping to figure out which model fits the best. So step 5, iterating, is almost like an exploratory analysis, if you want to think about it. But everything that I mentioned here is not exploratory until you get to step 5. There is a high chance that we're capitalizing on chance, p-hacking potentially in this sense as well. We have to sort of be careful about that, not make claims beyond it, but just so long as we outline our process, I think that's an important part. So those are the 5 big steps in the measurement model analysis, but then there are auxiliary components as well, right? So for instance, we may need to give everybody a score. In conspiracy theory land, for our example, that thing, I don't know that we need a score as much as I'd like to understand the structure of, I don't know why I'm giving a thumbs up here. I turned on the reactions because I was so excited about the answer being correct in the chat that now we're just stuck with them. But that being said, the score estimation part in conspiracies, we may not need that, right? Undergraduate students are filling out a survey about their beliefs on conspiracies. We're not going to go and try to figure out who's the biggest conspiracy nut or whatever, right? That's not important. It might be more important for us to understand, for instance, the structure of conspiracies. Are they unidimensional? Is there one driving force? Are there multiple sources of sort of misaligned beliefs that are behind them? It would be one of the questions we'd want. But if this were an exercise, maybe not in conspiracies, but we're looking at personality traits, or we're looking at cognitive variables, learning abilities, mathematics ability, Bayesian ability, we may want to provide a score like the ACT or SAT. And score reporting, score estimation is part of that. Furthermore, there's a whole lot we like to do once we get a score. How many of you have ever run analysis with a test score in it, somewhere? Independent variable, dependent variable. Happens all the time, right? It turns out those secondary analyses, we probably need to treat that score as some of missing data and figure out how to do that. So we'll talk a little bit about that as we go forward. Item evaluation. We may want to see if the questions that we asked behave the way we expect them to. So we want to see which ones perhaps are highly related to the construct we're trying to measure, which ones that may not be related at all that we can drop. We may talk about scale constructions. In this case, what we're talking about is sort of the mapping of where people might respond to variables would be. So in a conspiracy sense, for instance, the hurricane, this was sent by some powerful deity to punish us. So many people are saying no to this. You can imagine that someone would have to have a really, really high level of belief in conspiracy to have them not say no to that question, right? So that's sort of the idea. What does the scale look? What does it mean to be a certain level of the scale? If we're in education, or if we have multiple forms, we may want to equate responses onto the same distribution, or link responses. Link the forms together so that they're comparable. And then finally, we may even worry about whether items behave differently for different types of people in our sample. For instance, do men and women respond differently to conspiracy theories when we ask about certain questions? Or pick two different, multiple groups of, we can sometimes call this a multi-group analysis. So these are things that are very important psychometrically as well. Any questions on this process? Does it seem familiar to you? Mostly? All right. So if you recall our first lecture on measurement models, we tried to describe the model with a path diagram, right? And so often in the path diagram, we use that to describe our model. There are many, many conventions on how to draw a path diagram, but I'm going to use the following. A circle represents a latent variable, the construct we're trying to measure. A square represents something that's been observed. So if we had 5 items here, these were all in squares. These are the observed data. We hypothesize an underlying latent variable that is influential on each of these. In fact, if we were to observe it, this path diagram indicates it would be predicting the score for each one of these observed variables. And so the path model on the previous slide showed this one latent variable and showed 5 observed variables. Each line I just mentioned implies this relationship, implies a relationship itself, right? And so we could sort of take this path diagram and think of it this way. On the right-hand side, or on the circle side, our latent variable represents our theory. That's why we built the scale in the first place. Our construct should be there. Right? So if you can think about putting yourself in the shoes of this researcher that was in my class in the early 2010s, that person believed there was a tendency to believe in conspiracy theories, like a general conspiracy theory theta, conspiracy theory, the tendency to believe in it. And this was a continuum. that people with higher on the continuum would be more likely to believe in most conspiracy theories, and lower on the continuum would be less likely to. So that's our hypothesized understanding of what the world is. You might say something different now that we're, almost 15 years down the line from where I got these data, maybe more like 10. It might be the case that we know more about how people believe about conspiracies now, and there may be more than one latent variable underlying it, right? We might think about conspiracies that underlie government, or conspiracies that underlie sinister individuals, or, you name it, right? So that's the question, that's the theory part. And then there's the data part, right? So you collect data based on your theory. Your theory helps you build questions, it helps you build the items that people respond to, and you go and solicit the data from people, you get a data set, and next thing you know, you have data to analyze. So this is how I like to think about it. This type of path diagram sort of mirrors our model equation, right? On the left, at least in my screen here, we have data. That's right. This is the left-hand side of the equals, and the right-hand side is theory. And why I put it this way in more of a general sense is once we start talking about distributions for data or distributions for the latent variable, what we're doing gets a name, right? If, for instance, if we say our latent variable is continuous and it follows a normal distribution, and my data I collected also could be approximated with a normal distribution, then that's an analysis we often call confirmatory factor analysis, right? But if you change that, it's just slightly, and you say, oh, my theory follows a normal distribution, it's continuous, just like before, but my data aren't continuous, right? I only have 5 categories. I'm going to model those as a multinomial or a categorical variable. Now that usually falls into something we call a polytomous item response model. And one of those that would come to mind, one that's sort of a default in Lavon or M+, would be the graded response model, basically a proportional odds of choosing one category versus another. So one factor loading and multiple thresholds for the data. Right. What I mention that to you is when you think about this from a generalized perspective, it's that the process is still the same, right? I came up with a theory, I came up with a survey based on that theory, and I collected data. But what changes by label are the distributional assumptions, right? When you say factor analysis, I think both of these are normal. When you say item response theory, I think this thing's normal, that thing's categorical. If you say diagnostic classification model, or you think cognitive diagnosis, then I think this thing's Bernoulli and that thing may be something else, right? So there's all sorts of permutations of theory and data that cause us to move down modeling families, but it's all related to this idea of measurement and psychometrics in general. What do we think so far? Okay. So if you think theory side and you think data side, and again, on my typical equations, as we read equations, we have data on the left, theory on the right, usually. The theory side might have latent variables involved. But there may also be other effects as needed by the model, right? So we start with a basic latent variable model where we just put in the theta. We map it on to predicting our observed data, right? But what happens if perhaps we have design considerations that we have to go and control for? So for instance, maybe we have students nested in classroom. Maybe there's not just a student version of the variable, maybe there's a classroom version of the variable. That would be a random effect, right? Random effects we see in multi-level models like random intercepts, random slopes, etc. They can show up in psychometric models as well too. And it turns out random effects are very much like latent variables. We don't observe them, we give them a distribution, we just rarely think of them as the same type of magic that we've done. They're sort of control variables. Right? Nobody ever gets excited that their random intercept is super high versus super low. But if you take the ACT or the GRE, you get super excited if your theta is high, or you get not excited if your theta is low, right? But those two concepts are very highly related in modeling. But random effects help us control for dependencies that may be present that we need to control. That, for instance, by observations being nested within a nested design structure. Similarly, testlet effects may show up. Testlet effects are often coded as some type of random effect as well. And a testlet effect is an effect of that we're trying to control for where items may have dependencies beyond just the latent variable. For instance, if you remember any of your assessments from high school or junior high, a reading test would often make you read a passage and then ask you several questions about the passage, almost like reading comprehension. Right? Well, those questions may be related because the passage itself is unique to each, is the same. Right? So if you read 3 paragraphs on a topic, and that topic is at a very high reading level, let's say, a very difficult set of text, a complex set of text, that might have more of an effect on people than just their ability to read. It may be some type of contextual effect of the passage itself. So often we come up with what we call testlet effects to control for this dependency. Basically, can we measure additional deviations from the ability to read beyond just the questions we're asking? Is there something unique to the passage as well, too? And finally, you may have other observed variables that show up in the measurement model. So for instance, if you have a set of data that exhibits differential item functioning, right? It may be the case that that is part of the phenomenon that is just part of what you're trying to study. I don't fully appreciate it. When we think of actually, let me back up for a second. When you think of cognitive tests, when you think of mathematics, for instance, we want there to be no differential item functioning. We want what we call measurement invariance. We want all the items to work the same for all the people. And for math and for cognitive abilities, that makes complete sense. But if we get into topics of personality, if we get into topics that are much more nuanced, perhaps even conspiracy theories, I don't know. It may be the case that different people or from different types of groups may respond differently. And if that's the case, one way that we can try to bring about some type of equivalence between that, or even test for differences, is to include group variables or continuous variables in the analysis as well. In fact, my preferred approach to what we call measurement invariance is something that we talk about using linear models, basically. If you have multiple groups, the inclusion of a group variable, like we just saw in homework, and we saw in the example from previously, our linear model example, we had a group variable of diet group. Once we put that in the model, our regression line changed by group because we had that group by height interaction. Same thing happens in the psychometric model. If you're thinking, do I have different parameters by group? If you enter the the categorical grouping variable into your model, you'll be able to test whether the parameters are actually different from each other using the interaction between group and latent variable. So the theory side contains what we're trying to measure, but also contains everything that might get in the way of measuring it, kind of interfere with quality measurement. Questions on any of that? All right. Now the data side includes the outcomes, all of the outcomes. And more specifically, if you really want to be nitpicky, a function applied to one or more statistics of the outcome. What do I mean by that? Think of it this way. In our linear model example, when we put in our weight variable, our dependent variable, it followed a normal distribution. And we had to derive from the regression analysis what the mean of it happened to be, what the variance happened to be, right? So what we did was we looked at our regression model and we said, oh, this first part, that's the model for the mean. And we put that in the model for the mean. We saw, oh, there's this error term. We put that in the model for the variance. We didn't really apply a function there, but that's where we would have. When we talk about the mean itself being our regression coefficients times our predictors, if we have linear regression, we leave it alone. Sometimes we call that the identity function. It's like taking it and multiplying it by 1. But if we didn't have a linear outcome, if we didn't have a continuous outcome, like in our example of weight, which was continuous, if we had something discrete, which was, obese or not obese, something along those lines, right? we wouldn't be able to use a linear regression because that outcome doesn't meet our our assumptions of continuous normality, for instance, or conditional normality. So instead, what we would have to do is map it onto a binary variable. And the function that we would apply would be something like a logistic function, right? Where basically we have to take our mean, right, which in a binary outcome, a mean is between 0 and 1, and transform it into something that's continuous and on the real number line. And that transformation is taking the log of the odds. Again, even Apple is going to give me a thumbs up for that. The log of the odds. Don't use your thumb, Templin. Just use my finger. The log of the odds is what's needed to do it. So what are odds? It's probability over 1 minus probability. Just remember, probability is a mean. So that's the statistic of our outcome. What's the mean of it, right? And we take the odds. Probability over 1 minus probability gives us a number that goes between 0 and to infinity. And then if we take the log of that number, all the numbers between 0 and 1 in odds become negative in log odds. And everything that's above 1 becomes positive in log odds. And the odds of 1, which means an actual 50-50 chance of something happening, even odds, if you would call it, becomes 0. Right? So that's our function. So on the data side, we'll have outcomes. Particularly that function sometimes is called a link function or an inverse link function. A link function takes something like the mean and sends it to the continuous full number line. The inverse link does the reverse, takes the predicted value on the continuous full number line and sends it back to the probability space or some other space of the variable. We'll have, and as you know in Bayes, as you coded for your homework, as you're coding for your homework, as you saw in our last example, each outcome would have an assumed distribution itself. There's a key statistic for the outcome, usually the mean, and then some type of a link function as well. So it gets a little more complicated. And in Bayes, at least in this class, we're going to build each one of those by hand, right? We're going to code each one of those ourselves. So that's just like in homework, where part of the challenge was what goes where the mean goes, what goes where the standard deviation goes. We're going to have to do the same thing when it comes to each of these models themselves. The downside is it takes a little bit of time. The upside is if you come up with a measurement model that no one has software for, you really want to use this measurement model, but Levon won't do it or M+ won't do it yet. Guess what? Now you'll know how to do it yourself in Stan, right? To me, that's awesome. There is no limit to your creativity when it comes to psychometrics. And I say creativity, but really what I mean is the mapping of data onto assumptions, right? Okay. Questions? Again, this is very general, but we're just going to keep going here. All right, let's start with an example. An example for one outcome and one latent variable may look like this. On the right-hand side, this is theory, right? So here is our continuous variable. This might represent someone's belief in conspiracies, right? And in this class, I won't actually get into discrete categorical variables, in part because me teaching you Stan makes it so that Stan won't run them easily. It takes a lot of effort. But here's our belief in conspiracies. On the left-hand side, this is our data, okay? That sounds weird. That's y. Now let's unpack why y shows up in a couple different functions here. This function is, we basically say that's the expected value. Remember, expected value is another synonym for mean. So we're going to take the mean of our data conditional on our latent variable. So what that means is, once we are basically saying, what's the average score that we expect if we could observe a person's latent variable? What would be the average that we expect? And now, to that mean, we apply what's called a link function, f of this f function. Right? If the function itself is to do nothing, right? That's like taking our mean and multiplying it by 1. That shows up. We call that a confirmatory factor analysis. If this function says, take the log of the odds of our mean, we would probably use that in a logistic version of a model, a Bernoulli distribution. And there are many, many other different functions that we do too, but this is sort of the structure. And in this class, as it's a little bit more advanced, to talk about the generalized sense, I'm building it from this really general setting that will work, sort of lays out the idea of measurement models broadly, rather than saying these are factor analysis versus IRT. I think there's benefit to knowing the whole broad picture here. All right, questions on any of this here? I know for me, when I was learning it, when I started looking at this, I was just like, my eyes started rolling back. What does all this mean? And if you're like that, that's understandable. It's probably expected if you follow a pathway like I did. Not only that, it may be confusing. So, but let me remind you, I'm here to answer your questions. But just think, this is just the left-hand side of most of our equations in what we do. So if you've seen it, you may see IRT models get expressed a little bit differently. We'll get to those in a few weeks. But this is just the left-hand side. And I can help you disentangle what that means as we go forward. All right, jumping in, let's talk about the latent variables. The right-hand side, the theory in our model, are built by us. We specify them. We come up with why they're there, right? Not only that, we have to describe what their distribution happens to be. In Bayes, in our Bayes class, you know that everything we do has a distribution, right? The only thing that didn't have a distribution in homework or the example were the predictor variables. Well, in a psychometric model, particularly a very basic psychometric model, we don't have any predictor variables. We just observed Likert responses. We're trying to put them into a model. So we have to specify the distribution of our latent variables. And I will tell you this, that nearly all latent variable models have the latent variables follow a normal distribution. Right? So that's part of it. I will note that in non-Bayesian psychometrics, you often specify the distribution of the latent variable as well, but not always. There are times, particularly in if you're taking IRT class, you might say ability just exists and it's on some type of continuum, and you have to go and figure out what that continuum is. But most of the time, we give a distribution to the latent variable, almost always. So that's a very Bayesian idea, right? But once we say a latent variable is normally distributed, for instance, though, we then have to go and figure out what do we mean by its mean and standard deviation. Step 2, the scale analysis itself, right? There are multiple ways to do that we're going to talk about in just a bit. And actually, there's 2 main ways. I'll just mention them right now. One is to say that the mean is 0 and the standard deviation is 1. Sometimes we call this standardized factor or standardized latent variable because a standard, like a z-score, has a mean of 0 and a standard deviation of 1. That is what we're talking about here, right? There are other times where the standardized version of the model doesn't work well, right? So for instance, if we want to predict this latent variable that's normally distributed, it's going to become an outcome in what we would call a structural equation model. Well, we'd want to do that all at one time here, but the reality of it is once we predict a variable, remember that variance of it shrinks. It becomes a residual variance, right? We should explain what variance is. That's a problem if we fix the standard deviation of the latent variable to 1, because that becomes a residual standard deviation, and once we predict it. So there are times where we may want to estimate a standard deviation, and there are times where we may want to estimate a mean as well too, particularly in measurement and variance analyses. And so if we want those to happen, we have to make other constraints in our model. To estimate the variance side, we may have to set one item's loading to 1. We call that a marker item. Right? If we want to estimate the mean side, we may have to set one item's intercept to a certain value as well, like 0. And that sort of rescales the model itself. But we'll talk about those, again, a little bit more in depth when we actually build the models. Next, you create latent variables by specifying which items measure which latent variables in the analysis model. Right? So what happens next is, right, you're building this conspiracy theory scale. You say, I think there's 2 versions of conspiracy theories. One that involves the government and one that involves evil people. Right? So I might have 2 latent variables. I then create a set of items, and some items might talk about the government by itself, and some items might talk about certain evil people by themselves, right? That mapping of item onto which latent variable it measures is called the alignment sometimes, if we're in educational measurement. How well do items align to educational standards they purport to measure? In non-educational settings, if you're in psychology looking at like personality theory or so forth, we may sometimes call this a factor pattern matrix, referring to the pattern of results that came out of an exploratory factor analysis, like which items had the biggest loadings on which factors. But generally for me, and in the world I live in, the research that I've worked on extensively throughout my career is something called diagnostic models. We refer to this as building a Q-matrix. This is short for question matrix. This is an indicator matrix that has a 0, that has each item in the row, and each column represents one of our latent variables that we'd like to measure. And if an item measures that latent variable, the entry for that matrix gets a 1, and if it doesn't, it gets a 0. So the Q-matrix to me is what we use. If you look at the MERT software in R for item response theory, it describes Q-matrices for multidimensional models as well too. It sort of sticks around. So really, if you think of our 10 items in our conspiracy example, we'd have to go back and try to align those items to the latent dimensions. And technically, I'm not going to make us do this task in the previous year's class. I sort of did that, but since I've been gone for so long, I don't want to do that this time. But let's think about it. If you were to be the person who created these conspiracy items, you might think there are 2 latent variables behind them, right? One being conspiracy by government entities. Government here. I guess this might be government. This might be evil actor. U.S. evasion, that might be government, right? So and so forth. So what you would end up doing in this alignment task is to figure out which items mapped onto which dimensions. Right? And you may have heard before that good items are items that measure only one thing. Yes, generally speaking, that is true. However, for certain contexts of psychometrics, you may want an item to be more complex in structure. So for instance, if you're building a mathematics test and you're testing calculus skills, right? The calculus itself, for those of you who've taken calculus, and if you haven't, that's okay too. The calculus part is somewhat limited, but almost every part of a calculus test involves heavy, heavy doses of algebra, like in all forms. So if you're thinking about a person's ability to do calculus, and you want to talk about, let's say, differentiating, some type of equation using derivative, the calculus section of it, you'd have to disentangle from the ability from a person to do algebra. And so on that item itself, you might have some type of differentiation part for calculus, and then series of algebraic knowledge as well that's needed, sort of control for it. So I say that because in our task today, I would actually go put a 1 by certain things, the government versus non-government. If I were to go look at these items, I'd go 1 by 1 and put a 1 in each spot. It's not necessary to have a 1 only in each spot. An item can measure as many latent variables as possible. There's one other identification constraint we're going to get to in just a bit. But this is the task of alignment, right? Generally speaking, it's sort of a backwards alignment that we're doing now, in that I showed you the items first, and then we talked about what we should measure. But in your practice, and for the practice of those that you work with, it works better in reverse for what we just did in class. Meaning, come up with what you're trying to measure first, and then write items to measure it that are aligned to it. And at the end of it, you should have a matrix where a 1 appears if the item measures that factor, and a 0 otherwise. So you could think of us building a model that had 2 latent variables here, the government, conspiracy about government entities and conspiracy about non-government entities. Does that make sense? All right. So now, from Q-matrix to model, right? So once we have our Q-matrix, we can then build our analysis model out of it, right? The alignment itself provides a specification of which latent variables are measured by which items. Sometimes we say items load on to factors. You may have heard that before. So for instance, if I go back to here, let's say certain government officials. Let's say this item measures the government conspiracy factor itself, right? What we would say is this item loads onto the government conspiracy factor, or is aligned to. I prefer to say that this item measures the latent variable because it really reinforces what this item is built to do, is to measure a construct for us. All right. So the mathematical definition of either of these terms is simply whether or not a latent variable appears as a predictor for each item, right? So if you have a 1 in the Q matrix, right, if this were item 1 right here, you would see the first latent variable would measure it, right? Basically an equation with it. So what this Q matrix is doing is basically specifying which latent variables appear on the right-hand side of the equation for each of the items. Or put another way, which latent variables predict what the score of each item would be if we could have observed them. How's that sitting with you? So if you want to think about where I'm angling with this, I left you the last time we talked with efficient stand code, where we built one model at the matrix. Turns out later in class we'll incorporate a Q matrix into our model, and now we'll have efficient multidimensional measurement model code as well too. So that's where we're building toward. But I do like the concept of the Q matrix. All right. The model for the first item is then built with only the factors measured by the item being present, right? So this is our model right here. Left-hand side, again, is a function of the mean of the observation. The right-hand side has a few parameters. These parameters have different Greek characters than we would see in a linear regression. However, they are almost identical to a linear regression or a regression model, right? Regression coefficients. In that mu is often used to describe an item intercept. And we interpret an intercept in regression the same way we interpret an intercept in psychometric variable land, model land. It is the expected value or the predicted response for a person who has a 0 on all the predictors. In this case, a person who has a 0 on our latent variable. And if you want to add more context to that, if you said this latent variable's mean should be 0, because we have to specify the mean most often, this is also the expected response for somebody who's at the mean of our latent variable. So it's a nice way of thinking about what that happens. Lambda, in this case, is what we call the factor loading for the item. Factor loading, if you're looking for synonyms for it, and again, this is where we have a symbol for it. We can talk about what it means, right? For every 1 unit increase in lambda, and 1 unit increase in our latent variable, so a person going from 0 to 1 would bring about a change in expected response of lambda, right? It's the same meaning of our regression slope in our linear model from before. The 1 represents here, the first subscript is the first item. That's the loading for the first item of the first factor, the second subscript for it. Finally, theta itself, that is our latent variable for person P, and factor 1 that appears. And because this item did not align to the non-government entity, we don't have the second loading, the second latent variable in the model itself. But had it been there, we would have seen a plus sign. We would have seen loading, which would be lambda 1, 2, meaning the second loading for item 1. And we'd have theta P2 in there as well, too. Right, so the same intercept, but we'd have a different loading for each. Now, I will note, again, synonyms factor loading. You will hear it described as discrimination in IRT, the discrimination parameter. Discrimination parameter. I don't believe that the term discrimination parameter is really not a term that we want to be advertising a lot, but what it refers to is the ability for an item to discriminate between very small regions of the latent trait, meaning if that parameter is high, very, very large, you can quickly identify if a person's above or below that level of difficulty by if they answered the item with a yes or a no. That's where that term comes from. But factor loading and discrimination are synonyms. They mean the same thing. Another term for this you might call as a main effect. In the diagnostic model literature, we would refer to this as main effect, usually referring to our latent variable as being discrete, like analysis of variance might be. But what you will hear from me when I say factor loading, if you're used to item response theory, translate that to discrimination. I would call it slope, as we would in a linear model, but for whatever reason, slope does not tend to appear in psychometric literature. So factor loading is synonymous with slope, or main effect, or discrimination. All of those are the same word for the same concept. Cool? All right, keep it moving then. All right. We could actually put this into matrix algebra and make a model quickly. And this is where I was talking about before. What we did there is if we look at our model equation right here, and we think of our Q matrix, Q11 would be the element for item 1 and factor 1. And if I go back here, Q11 is 0. I'm sorry, is a 1. This is Q12, which is a 0. This is showing what the model looks like with our Q matrix involved, right? We set the value of Q11. That's our design. So we give it a 1, and this loading times latent variable shows up on our model equation. Q12, we gave a value of 0, so that keeps lambda 12 and theta p2 from showing up on our model equation. And again, I'm building it from the model and the matrix perspective, because in general what that means is if we were to take the diagonal, if we were to take this Q vector, right, which is just a 1 and a 0, and build a diagonal matrix out of that, we would arrive at this same equation as a function of the Q matrix and potentially our theta vector itself. Now again, that's a lot of matrix algebra. And actually, let me walk through it for you real quick. Lambda 1, this vector of all the loadings, has each of our lambda 1, 1, lambda 1, 2, and this T means it's transposed, so it's a 2-row by 1-column vector. The diag here of the Q matrix just is this matrix where we take a diagonal matrix and multiply it by our Q vector looking here. So the diagonal represents our Q vector along here. And then our theta vector here is 1, 2. And actually, I have the dimensions of this off. I have to fix this because this matrix in the middle is a 2 by 2, which means we need to pre-multiply it by a 1 by 2, which is actually lambda with not transposed, excuse me. But theta should be transposed to build all this up. So I'll fix that and get it reposted. Vladimir, I think this was wrong when I taught your class before. I thought I fixed it, but I guess I fixed it wrong. So I didn't fix it. But I tried. I just tried and failed. All right. So what that builds is, if you think about this from the whole Q matrix approach, if we have 10 items, each item will have its own model itself, right? Some items will measure 1 dimension, right here. Like everything that ends with a 1 here, theta p1 is a latent variable for the governmental conspiracy dimension. And theta p2 represents everything that's a non-governmental entity itself. So you can see each of those. So up to this point, we've talked generally about the right-hand side of each item's model. I will note that there are some models that get differentiated by constraints placed on these parameters, right? So the right-hand side, right, everything that's right here. For instance, a Roche model, so when I mention some constraints on this, often a Roche model is a model where we constrain each of our loading or discrimination parameters to be equal. And we estimate the variance of our latent variable. That would be one version of it. If we have a parallel items model in CFA is one where we also have all the loadings equal. We also have the residual variances equal. So their models can be differentiated, and the terms can be differentiated by mathematical constraints on this side. So I wanted to stop and say that. But in general, I find it easier to work with the linear model version of each item equation because it gives a nice, this context is right here. This makes sense. It's somewhat easier to implement too. And what I meant that latter part is how we do this in Stan, we're building it. All right, your first homework, you built the right-hand side where the left-hand side was just y. And you could go implement that in Stan. Well, now for each version of this model, we're going to do the same thing. We're going to have a right-hand side and a left-hand side. And you can envision we'll just have multiple things that we have models for. That's the part of tying it all together. So I'm building this around linear models, building psychometric models around linear models has really helped project this, what we're trying to do, onto Stan. And it turns out you have most of the knowledge of what you need already. There's a few other catches as we go forward. But after we build, I'm sorry, let me pause here. Does anybody have any questions about any of this? I know it's really like abstract. Like nobody would call this factor analysis, or nobody would call this IRT, and yet it encapsulates both. So any questions about this? All right, I'll pause. Pause is over. Let's talk a little bit more about the latent variable distributions. So after we have the Q-matrix, after we build that, the Q-matrix gives us the right-hand side, right? We then have to figure out a distribution for the latent variable. The latent variable is usually normal. Models that have normal latent variables most frequently are things like confirmatory factor analysis, item response theory, multi-dimensional item response theory. There's a whole bunch of unfolding models. I don't know if you've heard of those before. Those are kind of cool. Cool in sense of what it tries to do. Basically, the idea that there's somewhat what we call an ideal point on a continuum, and a person at the ideal point will answer a certain way most likely. But above the ideal point and below the ideal point, the probability might decrease. In this step, when we specify a distribution for latent variables, it's the same as building a prior distribution. It's literally a prior distribution of those latent variables. And I just remind you, from our last example from linear models, if the set of latent variables turns out to be multivariate normal, so if we specify a multivariate normal prior, that means by implication that each single latent variable follows a univariate normal distribution. Right? So if we have 10 latent variables, we could specify a 10-dimensional multivariate normal distribution. That would mean that each one of those 10 have a normal distribution by themselves. But remember, that's a prior distribution. Right? What we're seeking is the posterior distribution in the Bayesian analysis. Just a little bit more on latent variable distributions, then we'll pause for today, the end of the day. In general, any distribution can be used. That's the funny thing. Like we teach IRT and CFA with normal distributions always, but we could use anything. You want a Cauchy distribution latent variable? All right, Stan will do it for you. No problem. Put it in the model. You want a discrete latent variable? Stan has a little bit of a problem with that. It needs to be continuous in Stan. JAGs will do discrete variables. But non-normal distributions have been useful, but it's really complicated. There is a whole field of psychometrics that involves non-normal latent variables. Two of the most frequent, at least in my world, are Bernoulli latent variables, which is the diagnostic model idea, or multinomial or categorical latent variables, which are mixture models. So latent class analysis, growth mixture model, you name it, those are discrete as well too. But for our class, they'll all be normal. And at that, I'm out of time. So, any questions before we wrap up? No questions. Great. Two other points. Number one, office hours are tomorrow, 10 to noon for me. Vladimir also has office hours. I'd be happy to help you with homework or anything you'd like to talk about going on. And number two, on Friday, we'll continue with on Thursday, we'll talk about the rest of this. I'll also talk a little bit about project as well, too. So, thank you for your time. It's good to see you again. And keep doing the good work in Bayes, all right? All right. Have a good day. Take care.